Can start if you want.
All right. Hey, everyone. I'm Matt, and let me just start by thanking the organizers for giving me the chance to speak today, and thank all of you for attending. Now, I know you just heard a talk on op-rads, but I am going to do another one. Encore. So, maybe some of you know what op-rads are, or maybe you've given a presentation on op-rads in the past 5 minutes, but if you haven't, I'll just do a quick little overview of some things here, just so we're all up to speed. So when we're thinking about op-rads, you can do op-rads in different symmetric modal categories. You can work in the enriched setting, but for here, all of our op-rads are just going to be in set to make things very concrete and easy. So an op-rad, an ordinary op-rad, non-colored, will just have in all ends, so for all orders n, you'll have some set of operations. So you want to think of these operations as being these sort of multi-input maps that have a single output. And you want to be able to compose these different things together in some reasonable way. So if you have a whole bunch of different operations, you can stick them all together into something that seems reasonable. And you can set all of this up with categorical language, commutative diagrams and all that stuff. But we won't worry too much about that technical business right now. But there's also a notion of a symmetric op-rad. So a symmetric op-rad is the same basic idea, but if you have n inputs, then for all permutations, you need some sort of action of the permutation on the inputs. So you can think of this sort of like, tangling up all of the different inputs, like you're tangling up, I don't know, shoelaces or your headphones or something, and you need to get out of that some new operation. And the symmetric action has to play well with the composition, so you have some equivariance and things that you need to satisfy. But if you have all of that stuff, then you get a symmetric op-rad. And then the third type of op-rad that we're going to consider, which you've already seen if you went to the last talk, is the colored op-rad. And a colored op-rad is basically the same sort of setup, but now all of the inputs and the outputs are labeled by some kind of a color. So the inputs might be A1 to AN, and then the output might be B. And I'm going to use the notation for what follows. I'm going to have this notation here, where this operation is going to be in this set of operations. So here are our inputs, and this is our output. So this is basically how you set up op-rads, and colored op-rads also have some symmetric action on them. But that's not the only thing we want to consider. We need to consider algebras over an op-rad. So algebras of an op-rad are sort of like representations of groups. Like if you have a group, just an ordinary group, it's supposed to in some way represent some kind of symmetries of something. But if you're just given an abstract group, it's not super clear from the get-go what it is symmetries of. But when you take a representation of that group, it becomes very concrete. The symmetries of the group become symmetries of some vector space. In the same way, an algebra of an op-rad takes these abstract operations, and it turns them into concrete operations in some actual category. So your order n operations become actual operations from the n-fold tensor product of an object to itself. And there's similarly a notion of an algebra of a colored op-rad, where now your operations become maps from these tensor products of all the input colors, or I guess there's a little bit of an abusive notation here. On this side, the A and B are colors in your op-rad, and then on this side, they're becoming actual objects in your target category. Hopefully that's not too confusing, but you can probably get the gist of what I'm getting at, that your operations become actual morphisms in your target category. Okay, so the idea of this talk is that there's a way of constructing a new op-rad of interest from op-rads that you might already have. And this is obviously a pretty common theme in mathematics. You start with some mathematical construction, and then you want to be able to create other things like that. So, you take products, or you take coproducts, or quotients, or whatever. So here, the idea is if we start with some op-rad, and we also start with some small category, so here's our category, and here's our op-rad, we want to construct a new op-rad whose algebras are just the functors from our small category into the category of algebras of our original op-rad. So, for example, we'll see later on in the talk that one of the big examples of this are algebraic quantum field theories. So there's an op-rad which captures monoids. So the associative op-rad, if you take algebras over that op-rad, you just get monoids back. And an AQFT is basically some kind of functor from space-time category to the category of monoids. So you can construct that using oprads with this kind of construction here. So how do we set up our operad that we're going for? So the idea is for every object in C, so I'll use Greek letters to be the objects in C. For every object in C, we want to come up with some color in our new operad OC. So we have all of these objects in C, and these are all colors. And at each of these objects, what the functor wants to do is it wants to create an O algebra there, right? So somehow at each of the colors, we need to associate all of the ONs. So there might be more complicated ways of doing this, but a really simple way of doing it is basically just using generators and relations. So the idea is if we are looking just with a fixed object of C, just a fixed color alpha, all of the maps from n inputs of alpha to alpha should just correspond to the actual n arity operations in the original operad. So in this way, you kind of reconstruct the actual operad at every color in, or at every object in C. But then you don't only need that. When you're doing this functor, obviously the morphisms in C have to become actual O algebra morphisms. So we need a way of mapping between the colors in our operad. So that would be these maps here, where your input color is alpha and your output color is beta. And these things are supposed to correspond to the morphisms from alpha and beta in the original category. And I put equal signs here. Maybe that's a little bit misleading because these are not exactly equal to these things. These are more the generators that create the actual set of operations that you're working with. So once you set up all of these generators, there's a few relations you have to impose just to make sure that everything works out well. So first of all, one thing that we should probably note is that if you have morphisms in your original category C, so you have like F and G in your original category, both these things get carried through this kind of equation here. They're carried to some morphism or some like arity 1 map in your new operad. So maybe I'll just call those subscript O. So you need to impose the fact that this behaves well with composition. So if you have G composed with F in your category C, that thing in the operad should be the same thing as just if you compose where G and F go in the operad. And similarly, if you have an identity morphism on alpha, that thing should become the unit in the operad at alpha. So this is just a bunch of sort of technical pieces just to make sure that everything sits appropriately. But we need one more set of relations which are really, really important. And those relations are right here. So these relations here, and I used string diagrams. I don't know how comfortable or confident people are with string diagrams, but I like them because they look pretty much exactly like how I draw operad maps. So they kind of just have the same flavor. But the idea here is you can reconstruct an actual commutative diagram using this, but this is basically just saying, if you do the map F first in all of the components, and then you compose with some n arity version of beta, it's the same thing as doing the n arity version of alpha and then composing with F afterwards. So this is just an important diagram that you need to make sure that you have to make sure that the actual algebras you get are in fact functors to the O algebra category. Okay, so once you have all that set up, right now we haven't dealt with any symmetry. So this all works as long as you're not working with symmetric operads. So now let's try and introduce some symmetry to this thing. So the idea with considering symmetric operads is that the general operations in our new operad OC are something along these lines, right? So we have these pieces here where this is going to be something from beta, 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 beta to beta. And then you have like these individual pieces where you have alpha I to beta. Now, these pieces here inherit some symmetry from the original operad because these are generated by just the original operad's n arity operations. And so if your original operad is symmetric, that already carries some symmetric action on it. So we can inherit that for the central pieces. And then for all of these little one arity maps, there's no possible symmetry that you can have except for the trivial one. So we don't have to worry about that. So essentially, we can just define how the symmetry action works on a full operation in our new operad by just forcing it to satisfy equivariant conditions. So perhaps that's a bit rude or mischievous or something. We're not really paying attention to what these symmetry actions really look like, but you can kind of get away with it if you don't care too much about looking too deeply. So essentially what you do for the symmetric case is you say, I'm going to define the permutation action on any composition just formally, and then you just impose, again, certain relations that force equivariance to hold. So you can do all this, and then you end up having a symmetric operad whose algebras correspond to the functors that you want. So the only other case to consider now would be these colored operads. And the colored operads are really basically the same thing over and over again, but now we just end up with way more colors. Because the idea here is that, so for each color alpha, or sort of for each object alpha and beta in the original category, now we want to construct a whole colored operad. So if our colored operad has colors A, B, C, and so on, then what you need is for each object in the category C, you have to have all of these corresponding colors. So you would have alpha of A and alpha of B and so on and so on. And similarly, you would have beta of A and beta of B and so on and so on. So this is basically the underlying set of colors of our new operad when we're working in the colored operad case. So this also actually brings up why you need kind of the technical consideration of our category C being small, just to make sure that all of the colors that you end up with are still small. And also that the morphisms that you end up with in order 1 are still small. So you can set all that up. And then you have to impose, again, certain kinds of relations, but you can do it. It's just a bit of a hassle with the extra colors, but you impose some new relations where you're now fixing each of these individual colors. So this is basically saying if you're at the point alpha, then you can consider like something with alpha A1 to alpha AN inputs and some alpha B output. And these things are supposed to reconstruct the original colored operad that you're dealing with now. So you have all of these pieces. And then the idea is if you also have some beta here that has all of its individual colors as well, here's the alpha stuff, here's the beta stuff, alpha with the color A, beta with the color A, then you need some family of maps from all of the colors in A to the colors in B. And this is just how you actually define maps between algebras of colored operads. But to make sure that everything does actually turn out to be an algebra of colored operads, or an algebra of colored operad maps when you take the algebra, again, you have to impose certain kinds of conditions. So these relations are just the same kind of form that we had before, but now it's just a little bit more complicated because you have all of these individual colors showing up, but it's the same basic idea. And so if you set all of this stuff up, you arrive at exactly what we wanted, which is some operad OC, where now our underlying operad is a colored operad. And if you take the algebras over this operad, you get precisely the functors from your small category C to the O algebras. Now, why do we care about this construction? Oh, and also, yeah, sorry, I should just mention very quickly, again, you can inherit all of the symmetry stuff just for the colored operad case as well. But why do we really care about this construction? Is it just some sort of formal exercise? Well, one way of trying to motivate it is using algebraic quantum field theory. So in algebraic quantum field theory, perhaps unfortunately, or fortunately, depending on the type of person you are, I don't have time to go through all of the really fun details of what an algebraic quantum field theory is, but suffice it to say that in an algebraic quantum field theory, you essentially are dealing with functors from some category which is meant to be a space-time category, where the objects are essentially they're little patches of space-time, and the morphisms are inclusions of patches of space-time into some larger region of space-time. So you have all these little patches of space-time, and then at each patch of space-time, you want the algebra of observables. You want the things that you can kind of measure there. So if you set all this up, the way that you kind of set it up is you have functors from your space-time category to the category of monoids over some monoidal category. And of course, monoids, we can construct those with operands. The associative operand just gives you monoids. So from the construction that we just set up, using the associative operand and taking our new, like, whatever you want to call it, like OC operand, we just get from that new OC operand all of the functors of this form. So all of the algebraic quantum field theories. And you can see something of this form done in Benini-Schenkel-Boyka in their paper Operands for Algebraic Quantum Field Theory. They construct an operand, which is just the exact same operand that you get if you follow the construction that we outlined here. Or maybe I should mention very briefly that not only do you have to consider functors in algebraic quantum field theory, you don't just want to consider general functors, but if you care about physics at all, and I don't know how many mathematical physicists there are, but if you care about the actual physical ramifications of what you're doing, then there are certain conditions you have to impose upon the functors that you have to make sure that, essentially that you're not traveling faster than the speed of light and things like this. So if you do that, then you get a slight modification of the operand that we set up here, but you can still set it up in the same basic format, and then you arrive at the operand that Benini-Schenkel-Boyka had. Similarly, we can also consider. So similarly, we can also consider another kind of monoid. We can consider star monoids. So star monoids are basically just monoids who also have some kind of involution action. And from a physics perspective, this has to do with the fact that in physics, oftentimes you're working with adjoint operators and things like this. So you can set up these star monoids with star monoid operand, and then again, you can do the same kind of construction to get the functors now into the star monoid category. And if you do that, you get something very similar again to this Benini-Schenkel-Boyka work, where now it's in their paper involutive categories, colored star operands, and quantum field theory. So that's a lot of motivation from the physics background, but also there's, sort of a maybe more tame or however you want to kind of conceptualize it, set of examples where you can consider quiver representations, right? So a quiver, you can just consider it to be some kind of a small category. It just has dots and arrows in it. And a quiver representation just associates a vector space, or maybe you want to think about it as just a general module. You associate a module to each of the points, and you consider maps between the modules for each of the arrows. So essentially, you're just doing a functor from your quiver as a category. And of course, there is an operand, because there always seems to be an operand for everything. There's an operand that gives you modules over an algebra. So if you consider that operand and you do the construction that we just did, you wind up with these quiver representations. So hopefully that gives you a little bit of an overview of how you might consider this operand that we constructed popping up in nature. And hopefully you found this talk a little enjoyable. And if you have any questions, I'd be very happy to take them. Thank you.
Okay, thank you, Mark.